So I think we can probably start to see how we can really hang ourselves with java.lang.String. Before we start, here's a little quiz for you. And I want to get your attention just for a moment. You can go to sleep, back to sleep in a moment after that. So I've got 5 different ways in which you can, don't do that again. 5 different ways in which we can convert it into a string, right? The first one is just say double quote plus the value. That's the lazy way. That's, your colleagues will do stuff like that, the lazy guys. Then you've got integer.toString with the value, integer.value off the value, string.value off of a value, integer.get integer of the value. Now the question is, which one is the fastest way of converting an int to a string? Right? Who says the first is the fastest? The lazy people, sorry. No. Okay. Who says the second is the fastest? Whoa, okay. Okay, now you've only got, you all have to vote, so you've got to choose the next 3. Who says the third is the fastest? Okay. Who says the fourth is the fastest? All right. And who says the fifth is the fastest? Okay, awesome. Very good. Fantastic.
What about this one?
Louder.
And so we have here as well 3 ways to, in this case, concatenate string. Right? We have a classical one with a plus, or as Heinz said, lazy people version. Then we have a string builder, as it should, but unsized, and the one with a size. So, quick show of hands, who thinks the first version is the fastest?
What version of Java? Okay, that's a really good question. Thank you. I'm going to say let's say from Java 6, because how many of you are still using Java 6? Oh, right, okay. So from Java 6 with optimized string concat. So from then up to Java 11. So all of those. And just point out here that the arguments we're using are all strings, right? So there's no like ints and longs and other objects. It's all strings. So let's have a vote. Number 1 is the fastest. Okay.
What about number 2?
Okay.
And number 3, the pre-sized.
Okay. All right. Very good. Fantastic. Thanks for your participation.
We'll get back to that.
We'll get back. No, we won't. Okay. So, okay. So I want to take you back to the Dark Ages. No, way before the Dark Ages, when the dinosaurs roamed the earth. And when string was first invented, they had a char value array, right? They had an int offset and an int count. And the reason why they had offset and count, what did I say? I told you, 9:02 you'll come in. Exactly. Welcome. So the reason they had offset and length was that you could make very efficient substrings off a string. So if you've got a string, a very large string, you want to make into lots of little chunks, you could do it very efficiently by having the different strings have different offsets and lengths into the same shared array. So there's a really great idea for minimizing object creation when you're making substrings. Hash code was interesting. I'll show you the code in a moment. They used samples when the string was bigger than 16 characters. This was Java 1.0. Equals was always order n, so it always linear in cost, because they didn't check if the object was equal to this. Intern used a static hash table, so there was no chance of your static string ever being released from that. And string buffer was like, I like to call it a vector of type char. It's like a thread-safe version, and when you call toString on the string buffer, it actually shared the underlying char array with the string. So if you took a string buffer and you converted it to a string, they would both point to the same char array. And if you then change the string buffer, it would then make a new char array inside the string buffer, right? So this would minimize object creation. It's a really clever idea. So you don't have to make additional char arrays. This is what the hash code looked like in Java 1.0. And you can see that if the length is less than 16, they would go and add all of the values together and generate the hash code. And if it was bigger than 16, they would only look at 8 characters. So they wouldn't look at every 8th character, they'd only look at 8 characters. So if you make a string of size 1 million, okay, you couldn't in 1.0 because we didn't have enough memory, but if you could, right, then you would be able to, you'd only have 8 of those characters counted towards your hash code. So you had a fairly high chance of having different strings with the same hash code. This is Dmytro Vyazelenko. He's our chief disorganizer at jcrete, software engineer from somewhere anonymous.
Whatever.
You can guess where he's from.
Yeah, East. And this is Heinz Kabutz, jcrete unfounder, Java champion, groundbreak ambassador, and all other stuff.
Blah, 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 all that stuff, yeah. Now, if you want to look at what's happening at jcrete, have a look at that URL, jcrete.org. Also, we've done a special gift for you, 90% discount on our transmogrifier course. That's the URL up there, that QR code. I'll show it to you again in a moment. So I'll keep that URL, that QR code up for a bit. It's a really, really fun course. I bumped into somebody yesterday, and I used to have a transmogrifier course, basically Java.IO course, how to do Java.IO with design patterns and so on. I had a copy up on my Vimeo channel, and this guy said to me, "Why did you take it off? And why did you make it to be paid for?" And the reason is that the one that was on my Vimeo channel was really poor quality. It was the audio was PSTN, the video was like 800 by 600. It was just really terrible. And so I thought, let me rather redo everything. So I've redone it from scratch. Great audio, great resolution. Have a look at that. All right, let's look at Java 1.1. The fields stayed the same in Java 1.1. Hash code was still sampling. Intern moved to native code. And they did some weird stuff, like to uppercase, for example, added a weird edge case where the German SZ became 2 capital S's. Now in 2008, they actually added a new Unicode character for uppercase SZ, but that was long before Java 1.0, 1.1 and 1.0.
Long after.
Yep.
Long after one.
Yeah, long after. long after. And 1.2, they changed, they kept the fields the same, but they changed hash code. And this is what hash code looked like now. And you know these things, this thing called unit testing, right? A whole bunch of people had unit tests, and they assumed that string had certain hash codes, and all the unit tests broke. So people got very unhappy about the fact that the string hash code changed. And since then, they haven't dared change hash code. So the hash code that we had in 1.2 is still the same hash code you have in Java 11 and probably 12, 13, 14 ad infinitum, right? And now, instead of looking at only 8 characters, they look at every character. So it's gone from a constant time, order 1, to a linear time calculation. Something else is they've got the comparable interface now. So Java 1.2, you can sort things. All right. Now, there was a book published in Java, when Java 2 had just been released, called The Performance and Idiom Guide. This was like a precursor to the Effective Java book. It was like a combo of Effective Java and Java Performance Tuning book. So it was a good book for the time, a good book at the time. But the problem with performance books is that they go out of date really quickly. Because like every 6 months, then things change, and the laws you had before don't apply anymore as the new version comes out. And a very large chunk of the book was about when you have a string as a key, you should never use a string directly, but you should wrap the string with another object and then cache the hash code of the string inside that object, so that you don't have to do a linear calculation of the hash code. And after the book was written, Java 3 came out. Oh, wait, before I do that, let me just go back a step. And this whole idea of caching hash code seems like a really great idea until you think about it a bit, because when you cache a hash code inside a key, you're assuming that you're going to keep the key. You're assuming you're not going to throw away the key and regenerate the key, right? So if you do that, then caching the hash code will work. But if you don't keep the key, if you throw away the key and then regenerate it to find the value again, then it doesn't help you, because you have to then regenerate the value, regenerate the hash code. And as a side effect of that, if you are going to keep the key, why don't you just keep the value, right? So it doesn't help as much in practice as people think it will. So this is a very slow key, right? The hash code waits 100 milliseconds. And if I put 30 keys into the hash table or hash map, how long will it take? This is not a trick question. Who can tell me? 3 seconds, exactly. It's not going to take more. It's going to take 3 seconds because each hash code gets called exactly once. And when and the hash code gets cached inside the hash table as well, and inside the hash map. And when you get 30 times again, it's going to take 3 seconds, not longer. All right. So, pardon, sorry?
Assuming no collisions?
No, actually not, because even if there are collisions, they don't use. They're going to use the cached hash code of the node and dot equals. Right? My dot equals is fast. Right? Okay, now we move to Java 1.3, and there they actually decided to cache hash code inside string. So we had offset, count, and hash. And the whole thing of mutability, from an external view, it looks like it's immutable. But actually, is it really? Because hash changes, right? Now, there's actually a benign data race in string now. It is a data race, but it's benign. If two threads call hash code at the same time, they are going to both calculate the hash code, because hash starts as 0. You see, it starts uninitialized, which means it's 0. So if they both call hash code at the same time, it's both going to be 0. And then they're both going to do the calculation. But that's OK, because they both will come to the same conclusion. The answer is?
42.
That's right, 42. It's got to be 42. So because it's the same hash code, it doesn't matter the fact that in which order they write. An int is a 32-bit value, which means it's going to be an atomic write and read. It doesn't matter how many threads do it at the same time. All right. Now, look at these strings. Beautiful strings. What do they have in common? Yeah, same hash code, same length. Yeah, that's right. They have the same hash code. And in fact, they all have the hash code of 0. Okay? Quickly, take a photo. Well, I'll show this one so you can quickly go and hack something. Now, I actually wrote like a little program to find these things. I've tried lots of different approaches. Did it also in parallel, brute force, because you can do like a reverse algorithm to find to generate a string with whatever hash code you want. Joe Darcy wrote an article about that. But I wanted to find all strings of 7 character length with an alphabet of A to Z, lower and uppercase, that had a hash code of 0. Now, the significance about hash code 0 is that if you look at the algorithm that they use for the calculation, the hash is 31 times the previous hash plus the value. So once you get to 0, you can combine them together, and the answer is still 0. This is not true with hash code 42, because when you get hash code 42, if you add another one, it's not going to be 42. It's going to be something else, right? But if it's 0 and you add them together, you end up with hash code 0. So I want to show you something quickly, why this is so bad. And so I've got a string DOS over here.
In fact, it's even worse than that.
Why is it worse?
Because you can take any string in the world and then add little one with 0, and then it's 0. So you only need to, or actually start with 0 and add anything to it. Doesn't matter what you add. You don't have to add the zeros ones, right?
No, it's not exactly right, because you can at the end get 0 by adding some characters.
Because it adds it doesn't multiply.
It doesn't, exactly. It adds it, doesn't multiply.
Yeah, okay.
It's not rehearsed. This is just trying different things. So here I've got a bunch of different hash codes, and I basically do combinations of them, of different strings. So I'm generating a whole bunch of strings and then putting them into a hash map. So in order to do this, I'm going to just, wait, let me just go back for a second. I'm going to start with Java 6 and Java C, I was going to Java C, Playground, Hasher, String DOS, and this is all in our, we've got a Git repository for this. And now I'm going to say Java EU, JavaScript Playground, hasher string DOS. And you can see now, as the number of elements in the map get bigger, you have a lot of collisions, becomes a linear search through the map. And because I've got a loop of size n, and each lookup is linear, it becomes quadratic. You can see that as we double the size, it becomes 4 times slower, approximately, right? So it goes from like 1.5 seconds to like 3.6 seconds. The next one's going to be 12 seconds. It's going to take too long, right, to do this. Okay, so this is quite interesting. I'll run it again in a second. So the bucket collision, when you had a lot of bucket collisions, it became linear. And the problem was that this happens very easily when you've got hash code of 0, because you can make an infinite number of different string combinations, but just paste them together. And that's the unique characteristic of 0. Java 1.4, same fields as 1.3. They've now got an interface called char sequence. We'll get back to that in a moment. That's interesting as well. And they've got regular expressions if you want. If your code's running too quickly, you can use those. Now, this also, if you take this code here, system.println hello plus arguments, and then hello over here with, in Java 1.4, this got compiled up to 1.4 to new string buffer.append hello.append args .toString. And this would then, it would start as an array of 16, and then eventually, once you say toString, as I said before, it shared the char array with the string. So you wouldn't have to make another char array. And so in those days, if you pre-size a string buffer, you would then create the minimum amount of objects. 1.5, same fields as 1.3, but they marked them final except for hash. They also added something called code points, so 32-bit characters, and they replaced the synchronized string buffer with the unsynchronized string builder. Now this was interesting because the first side effect of that is that they didn't share the char array anymore. So there wasn't a shared char array. So if you made a string builder and you then said toString, it would then make a new char array for the string. So this was a bit more costly. The second side effect is that actually when you had to recompile all your code from 1.4 to 1.5, because the old code would have used string buffer, which was a synchronized version, and then 1.5 started using StringBuilder, which was unsynchronized. And what was interesting about that is that they solved a specific problem, which was string buffer, by having another class. But in Java 6, they actually solved the problem generally by eliminating synchronized when you don't need it. So they didn't need to do this. They could have just left it as string buffer and optimized it behind the scenes. Then they would have saved themselves that work. Java 1.6, not much change since Java 1.5, but they had compressed strings, which were kind of funky because on the fly, you could change a string, the string could change to use byte arrays rather than char arrays. So your reflection code had some real problems with that if you use reflection. Also, if you were trying to profile your application, you had to now look for byte array sometimes and char array sometimes. It wasn't so clear anymore which one to use. But the byte array only happened when you used a 7-bit ASCII value. So it only worked for the Americas. And the Germans were upset about that. They were like, why can't we use ASCII anymore? You know, anyway. So the other thing which was even more significant was optimized string concat, which they added in Java 6. We'll talk more about intrinsics and things like that. And this is interesting because the char array could in some cases now be shared automatically between StringBuilder and string buffer and string. Okay? So it became really optimized and much, much faster than before. Now, the answer to the quiz before was, it's all exactly the same, right? And it didn't matter from Java 1.6, if you use optimized string concat, from Java 1.6 up until Java 11, it's all exactly the same speed. And so what these figures mean, it means, first of all, okay, like the difference between 61 and 57, that's just a rounding error. That's not significant. But it's all exactly the same number of bytes. So you can see it's compiling it to the same. The 208 is a bit more than 200. You'll see why in a second. when we look at Java 7 structure. So it's a little bit, it's about the same. And then in 11, it's 120 bytes. And it's a little bit slower, and I don't think so. Do you remember why? Was it? Okay, we'll see. We'll see later.
We can do that.
But the quiz number 2, the answers, it's all exactly the same. So pick the first one because it's the easiest to do. And the other advantages we'll get to in a moment.
As long as you use strings only.
As long as it's only strings. If it's not strings, there's a big difference, which we'll see later. Java 7 threw away the idea of offset and length, right? So they made the char rate to be only exactly what the string is. So this was great if for example you didn't know how to code and you wanted to make a substring of a very large string in order to save memory, because we know that doesn't actually save memory. So what happened here is that they now made a new string with a new char array. There's also something funky. There was actually a constructor added, string with a char array and boolean unshared. Now this was a package private constructor, I think, so you couldn't call it from outside. Also, there was a class called shared secrets where you can actually use that to construct a new string that shares the same char array as you pass in. So if you've got a char array and you want to make a string from that, you can just use shared secrets.getLangAccess.newStringUnsafe. This also works in Java 8. The function is still around in Java 9 and 10, 11, but it doesn't work anymore because, well, okay, we'll see why in a moment. But substring had made lots of char arrays. Okay, so if you like want to break up, if you have a large string of 1 million characters and you want to tokenize it into lots of little strings, it's going to make lots of little char arrays. And if you want to see how to make a subbable string alternative, have a look up on newsletter 230.
But that was done on purpose, right?
It was done on purpose.
Out of memories. So if you have like a big XML file and you get your ID out of it, you're gonna drag the whole XML file with you in the versions up to Java 7. And Java 7 they avoid that. And Java is not unique in this respect. Like V8 from Chrome, they went back and forth. They did it like shared approach on the substring to beat the benchmarks. Then the next version they changed it back because of the out of memory, and then the community forced them to make it shared. So like, you know.
It's like benchmark driven coding.
Benchmark driven development.
We're faster. Fantastic. All right, Java 8. Yeah, one more thing. Sorry, I missed this. This is actually quite important. So Java, we saw this denial of service attack early on, where I had this hash map and I gave it a whole bunch of strings with size with hash code of 0. They actually have an alternative hashing function inside string, it's in Java 7, that is used for hash maps. And the interesting thing about this, it's first of all a better calculation, and secondly, it is slightly randomized so that every time you start the VM, your strings are going to give different numbers, different hash 32 numbers. So it's somewhere with system nanotime or something, it uses something to make sure that that you can't predict which strings will have size 0 on that one. I always thought this was on by default, but I discovered 2 weeks ago that it wasn't when I was preparing for this, that it was there, but nobody knew about it, right? Or maybe nobody used it. And so there's a special thing, -d JDK map alt hashing threshold, which I'm just going to copy and paste that because I want to remember that. And if you use that, then you can actually use a different hashing mechanism, right, for your hash map. This is Java 7. I took it out in Java 8. We'll get to that in a second. So if I take Java 7 and I call it normally like before, it's exactly the same, right? It gets slower and slower and slower and slower and quadratically slower, right? Well, linearly slower for the lookup, but because it's
quadratic complexity of the whole thing.
Of the whole thing, exactly. And if I run the same thing with this special setting, now the threshold is 512, which says once my table size is bigger than 512, then we're going to start using this alternative hashing mechanism. Okay? So it starts off at the same speed, and it slows down, and once it gets past the threshold of the whole table, look at that, brilliant. So it's now much, much faster. Okay?
Now we're back to constant lookup, right?
Yeah, constant lookup.
order one.
Exactly. Because the strings are being, I mean, I'm hitting the pain point by giving it all the right, that particular string. So, but this was again a very specific solution to a problem, a very specific one. Just like when they changed string buffer to string builder, it was very specific to one particular problem. In Java 8, they got rid of that. It was a good idea, but people got unhappy by the fact that the hash maps were not in the same order as before. Assuming that they have an order, right? They go like, oh, my tests don't work. Well, your tests are wrong, right? But they still get unhappy. We don't want people getting happy. So we have, in Java 8, a whole bunch of things. First of all, the hash 32 is gone. We've got static methods for joining strings, which are quite useful. We also have deduplication of char arrays. What deduplication means, we'll get to in a second. The last thing is that they fix the problem with denial of service attacks in a general way for Java 8 onwards. So within hash map and concurrent hash map, I don't know if did that fix hash table, do you know? I'm not sure. No, I don't think they did. But for hash map and concurrent hash map, for sure, they fix the problem by having a tree when you have too many bucket collisions. Right? So any key that you use should, from Java 8 onwards, have hash code equals and comparable. You should also implement comparable because that's used to build the tree. If you don't have comparable, you might not get that brilliant performance. So let's run that little demo again with Java 8. Java 8. And I don't need this setting anymore that doesn't do anything. And you can see that as we increase the size, the performance increases logarithmically. So it's a logarithmic performance. It's log n. So it gets a little bit slower. Every time we double the size, it gets a little bit slower, but not order n.
But it's slower than Java 7. Come on.
It is slower than Java 7, but only because they all are sitting in the same bucket, right? So there is still a tree. There's still something. Now this, okay, so something which is unfortunate is that you can expect a slowdown in general with general keys. You can expect a slowdown going from Java 7 to Java 8 of factor 3. Okay, for two reasons. First of all, you've got this binary tree structure that needs to be maintained and built. And secondly, they've got a rehashing or a hash mechanism inside the hash map that used to be very good in Java 7, and that's not so good in Java 8 anymore. But then we're going off topic. So let's go back to string. Right? And by the way, this performance is going to be similar for Java 9, 10, 11, 12, 13. Well, actually, I'm not sure about 12, but 9 up to 11 for sure. It's going to be very similar. All right, deduplication. Since Java 8.0.20, and I must say that actually, when I first heard about this math of having a new version every 6 months, I was a bit disturbed. But now I love it because it delineates much better what happens with different versions. See, before we had to know somebody's in Java 8. Well, is it 8.0.20? Or is it 8.0.36? Or is it 8.0.45? Or is it 8.0.72? Which version of 8 are you using? Whereas now we've got 9, 10, 11. It's much easier to remember what's in what. So, for example, string deduplication was added in 8.0.20. And I was speaking about this.
Yeah, yes.
Okay. I can't remember.
But it's only for G.
Okay. So this only works for when using a G1 collector, and you have to turn it on specifically by saying plus use string deduplication. And what happens is that if your string survives a number of collections, it then gets deduplicated, which means you share the same underlying char array. Now you can see here I'm creating two strings. They both are pointed to the same object. Now my thing doesn't work anymore.
You crashed it.
I crashed my thing. Okay, ignore that circle. Wait. Go away, circle. Crash the circle. Okay. How do you kill that circle? How do you kill the circle? Wait.
Is it on the screen? Or is
it's on the screen now.
Can you wipe it off?
No, I can't wipe it off because now it's on there. Okay. We'll have to do a kill -9 on Logitech. That's a good idea. Grep dodgy. Whoa. Ah, okay, I think we, like, the circle's gone. Whew. Sorry about that. I think the circle was garbage collecting.
And it had to survive so many collections.
Yeah, exactly. It was trying to do deduplication. So what happened here is that I've got a string, two strings, which point to the same char array. But when you make a string with a char array, it makes a new copy of the char array, so it becomes a new one. And then what I do is I use reflection to read the actual char array. And you can see before the GC that it points at two different char arrays, and then after system GC is called, after some time, it gets deduplicated, and now they actually are using the same char array for both of them.
Randomly chosen one of them.
Randomly chosen one of them, exactly. It's not deterministic into which one to choose. Let me take yours. Thanks. Now, deduplication can save you some time, but there's also a cost involved in doing the deduplicating, right? Because of course you have to find the strings which are the same and match them up somehow. So it's not completely for free, and it only helps you when your string is, I think it's bigger than 4. Is that right? I think it is, because let's say, for example, new string. So you've got a new string, hello world. Let's say Java 8, 64-bit oops, which means your object header in OpenJDK is going to be 12 bytes, object header, plus the value pointer is 4 bytes, plus the hash is another 4 bytes. It's actually 20 bytes, but it gets rounded up to 24 bytes. Then the char array is 12 bytes for the char array, plus the 12 characters for hello world is 12 times 2 is 24, plus 4 gives you 40 bytes. So the total is 64 bytes. Now, the deduplication here will save you 40 bytes automatically. You could also use intern, but that has a lot of problems, right? Don't use intern. Don't use intern. The intern table, first of all, is a fixed length table. It never grows. So if you make it too big, you're going to have performance problems. In Java 9, you can find out what is in your string table, in your intern table with J command. J command minus PID's VM string table shows you what's in your string table, and then you can debug that further with info, with minus verbose. You can also make your own concurrent hash map and to save your memory, but that means you could then basically do your own intern. Problem is, you must be careful that you don't have too many duplicates, otherwise, too many unique strings, because otherwise you create a memory leak there, and then we have to fix it.
Basically, you can build your own deduplicator based on a hash map, like a hash map or concurrent hash map. And
Yeah.
do it your own.
You can build your own intern, not your own deduplication.
Well, duplicate. Well,
Yeah, exactly.
canonical whatever. So there's only one. Yeah. Okay, so we are now in the parlance of Java 9, 10, and 11. The strings all the same, but as you can see, the char array is gone. So we have a byte array and a byte coder. So what's up with that? Well, actually, this is there's two important chapters down there. So one is about compact strings. So right now, so unlike Java 6, right, which try to do 7-bit ASCII compression on the fly, now it's a source level compression. So before we had like UTF-16 encoded values, so it was a character and 2 bytes for each. Now they decided to say, okay, if we have a value which is Latin 1 encoded, it can fit in a byte, so we can save some space by doing that. But it also means that your character array is gone. And it's not just a string. All the classes around string, StringBuilder, StringBuffer, all the helper methods work with byte array now.
So if you're doing profiling, you need to look for your byte arrays, not for your char arrays anymore.
Yeah, char arrays are gone. So before the char arrays were dominating thing, now it's a byte array. And the coder defines in which encoding the string actually is. And the size of the string didn't change, even though they added one more field. So let's talk about one of the features. I think it's JAP 280, Indify String Concat. What they wanted to do, they wanted to optimize string concatenation. And up to Java 8, string concatenation was either compiled to StringBuilder or 10/14 was StringBuffer. But it was a compilation level operation, which means Java-C would generate the code, and it will stay like this forever until you recompile. So they said, well, that's not good because JVM cannot optimize this code. So because it's hard-coded in the generated bytecode. So what if we can do it better? And to do better, they decided to use invoke dynamic. So essentially, instead of doing put in a string builder code, they just put an invoke dynamic instruction which just points to something.
Before you go there, just go back one.
Okay.
So what we did was we spent way too much time over the last 3 weeks doing benchmarking. It's always a bad idea, because once you start, you just can't stop. But we found so many things that were interesting that we just kept on going. And you can have a look at our benchmarks by looking at github.com/kabutz/string-performance. So they're all there. Also, some of our results are there. You don't want to observe all the results, but like the summary of the results are there. But you can run it yourself, and you can see how it runs in your systems. Okay, do continue.
And the slides are there as well.
Yeah, the slides are there
slides.
also. Yeah, the slides are there too.
You can get everything from there.
Yeah.
Okay, so let's look at some results. That's another benchmark. It's a string concat, but this time we don't concat just string parameters. We concatenate and mix things, including ints and longs and stuff. So this is like doing mixed data type, still string concatenation. So what we want to do in this benchmark, we try to compare lazy like string plus, string builder. There is a concat method in a string, which was surprising to me that there is something like that. Did you know about it before? Then there is a message format and format. And what you can see that in all the versions until Java 11, that size string builder was the way to go. So if you knew upfront what you are adding and you could calculate the size of a string, that would give you the best performance.
Just a comment on that also. This is like our quiz 2, except that we're using non-string parameters. Right? So all those that put up their hand for the first answer, you are correct from Java 11 onwards. Going forward, if it's not strings, if it's anything but strings. And if you put up the hand for the third one, you were correct before Java 11, before Java 8 and before.
So as always in performance, the answer is it depends.
It depends, yeah. What version?
And it was
a really good
question.
question. Really
What
great
version?
question, absolutely.
Okay.
And also look at the last one. This is string.format using regular expressions with %s and stuff. And I did a tweet asking that question 2, quiz 2, to my general audience. And Brian Goetz, the architect of Java, told us that format will soon be the same speed. Not yet, though.
I mean,
one day.
There is no reason why we cannot use the trick of invoke dynamic on plus. We can use it in other places, like
Absolutely.
format.
Absolutely.
Like this.
So, but we don't know when that's coming, but that's the promise of in the future. It's a future, completable future.
Yeah, okay, so they replace that. We have super cool, so plus is the way to go.
Yeah.
But it's not that simple.
No.
So there are actually 6 strategies to do string concatenation. There's of course one is the default, method handle inline sized exact to be precise, but actually 2 groups of strategies. So one group is a bytecode generator. So they generate bytecode on the fly, install a new class using unsafe, and it's essentially a class with a single static method, which has the logic of the concatenation in it. And the second group of method, it's method handle combinators. So it's like 3 different versions of how to do method handle combinated. And 5 of these strategies, they only rely on string builder. This is basically a wrapper around string builder, like before. So like BCSB is like bytecode string builder is exactly like old Java 5. So it's an unsized string builder. The sized versions are funny though, because these 2 different groups of methods use different sizing. So string builder size basically says everything that is an object or a string converted to string, and we do the length of it to know the size. And for the primitive, we take we call it.
Just a guess.
The worst case scenario, for example, let's assume it's a long, so it can be up to 20 character long. So we just assume it's the worst case scenario and size it like this.
And int is 10 because it's from minus 2 billion basically, so it's 10 characters.
Yeah, so like mean value, the negative was minus some sign, and exact sizing it's even weirder because each argument is first converted to a string using string.value of. Then they're going to size the string builder, and then they're going to add strings there. which sounds absolutely awful because the overhead of creating all those strings. Well, it's not that bad, we'll see in a second. And the method handler ones do similar, but for whatever reason, the method handler approach, they decided in a sizing approach to also convert floats and doubles to strings prematurely. Unlike guessing, and the exact sizing does totally opposite. For the remaining primitives, they calculate in exact value. For example, for Boolean, they would say, is it true? Then it's 4 characters. Is it false? Then it's 5 characters. So it's really, but the default strategy is very interesting because they said, well, what we create in the StringBuilder.String going to create a new byte array to create a string. There is no sharing. So why don't we create a byte array and write to the byte array directly?
So what does performance look like?
Well, let's have a look. Let's compare them. So the default strategy is 1 to 127 nanoseconds and creates 152 bytes. And this is exactly the size of a string. And going down, basically, all of other strategies are way worse.
So the last one is the old one. That's Java 5.
Yeah.
It's like 300 milliseconds. It's almost twice as slow as the
2.5 times. 2.5 slower.
And it uses 500 bytes, where the other one's 152 bytes. It's a big difference.
Yeah, it's like more than 3x in memory saving.
Awesome.
Okay. Let me go next. String concat. I already told you about byte array. There's of course also a kill switch where you can turn it off.
Why would you want to do that?
Well, because there are some interesting caveats to the thing. You notice for example, just one example. If when you create a string from the character array and the compact strings are on, which is a default in JDK 9+, there is an attempt to compress a string. So first the byte array is allocated and they start compressing. If along the lines they find a character that doesn't fit a single byte, they have to throw away the byte array, allocate a new one. So I have benchmarks in my other talk where I clearly show that actually degrades performance. You allocate more garbage with a string. So there are some cases, edge cases, where compact strings will not do. If you know that your application doesn't have any Latin 1 encoding, you have like Japanese characters, you better turn it off. Yeah, and this is just an example what an effect on that. As you see, when we turn off compact strings, clearly the number of bytes allocated increases. So it's just more stuff. And if you can fit, and this example, everything is compressible, so that's clearly shows this.
What's interesting is that in some of them the performance isn't that different.
Yeah, and performance-wise, it's basically like almost rounding error.
Yeah.
We're looking at this. It's really nothing. Okay, so if we talk about string, we have to touch on intrinsics. So if you look at the Java 8, this is just a glimpse of intrinsics, string-related ones. In Java 8 and in Java 11, it doesn't fit on the screen because of the compact strings. So now essentially there is twice as much code as it used to be. There is code for Latin 1, there is code for UTF-16. It's double this, and of course there's a double amount of intrinsics going on. So for those who know, intrinsics are either specially crafted assembly or compiler IR that is installed instead of the code. So if you look at the source code in JDK and you look at some of the code that is intrinsified, for example, if you look on the equals on a string, and you see interesting things. We compare the coder, for example. There's another optimization. So if two strings have different encoding, they by definition cannot be equal. So that's like an immediately exit from the equals method. But if they are, then we have to choose either Latin 1 or UTF-16. And for example, if you look in the Latin 1 implementation of equals, you see this magic annotation, hotspot intrinsic end. So you would think that the code is executed is the code you see on the slide. Actually, it's not. It's replaced with intrinsic. The catch with intrinsics, though, is that they are sometimes platform specific and CPU architecture specific. So in some cases, there might be the Java code executed. But in other cases, it would be something else. So let's compare. Okay, that's another new method added in JDK 9 where for arrays comparison, arrays mismatch, also intrinsified heavily and vectorized. So let's compare the three things. Calling string equals, calling hand-rolled, which is a copy from Latin 1 comparison, and the arrays mismatch. And as you can see, with the length increase, string equals essentially, stays more or less the same, but the hand-rolled version degrades really, really fast. And the reason for it, in the hand-rolled version, we are working 1 byte at a time, versus is in string equals and a mismatch, they are vectorized, so we're working in memory in bigger chunks.
Now actually all methods are order n. All of them are order n. But there's some overhead in doing the intrinsics. So we tried out with very long strings, like 1 million characters, and you can see that it's linear. So they're all linear, right? Yeah. But string equals is much faster than hand roll because of the vectorization.
Absolutely.
Oh, also something else, that deduplication is not taken into account with string equals. So if you have two char arrays with the same value, it's not going to be taken into account. So, lessons from today. Don't forget to vote as you walk out. No, forget that. What you need to do is you need to always use plus rather than StringBuilder. Avoid using intern. Remember that hashing can be expensive. Also, strings since Java 9 use Byte Array. And if you want to know more, have a look at our GitHub repository and grab that URL if you want to get a big discount on the transmogrifier before 10 o'clock today, so another 15 minutes. Any questions, please come speak to us. I don't think we have much time.
Yeah, we're out of time, unfortunately.
Out of time. Unless there's a very quick question. Anybody?
No.
So
Okay.
the classes are